Let's have a look. So we invested quite a bit of our time yesterday discussing the odds measurement, where we're looking at the ratio of something happening against that same thing not happening. Quick reminder, we are attempting to model a response variable that can only take one of two values. Yes, default, no, default. The probability of defaulting is, or at least our model is related to, in this very simple example, to the balance, to the size of the loan itself, which this data set would appear to be tied to credit card debt. And we created this relationship where the odds is equal to that's Euler's constant, E, to the beta naught plus beta 1 x. And we're probably going to start looking into how we would actually determine beta naught and beta 1. Going back to chapter 3 in simple linear regression, where we also had two parameters. In fact, we denoted them using the same notation. The approach was the one most commonly found in textbooks and used by practitioners, which is the method of least squares. Least squares is designed to minimize the residual sum of squares. Now, given that we're working with qualitative data, where the outputs aren't, if you will, on a continuum, but there's a very clear demarcation line, it's 0 or 1, to be interpreted as the probability of default given a specific balance. 0 means does not default, 1 means defaults. And you can include some kind of cutoff, or should we use confidence? I'll call it cutoff, where you would say, for instance, right, anyone, the bank will consider anyone, I've picked an arbitrary probability value over here. Anyone that the model is suggesting has a 20% probability of default or less, as does not default. Anyone else, but this is arbitrary, so you could just as easily place it over here or place it at the 50% mark. If we take logs on both sides, so we're taking log to mean the inverse of e to the, can see this in Desmos. I'm sure you're all up to speed with your logs, but for what it's worth, the book writes log, but it means log base e. So just simply a case of, just as we learned that dividing by 5 inverts multiplying by 5, or square rooting to an extent inverts x squared. Log base e, which the book shall simply denote by log, dropping the base, inverts e to the. So what's going on here? Well, what's going on is that the model, the curve, the blue curve that we're going to fit doesn't take values higher than 1 or lower than 0, unlike linear regression. in terms of it is consistent with the convention of probabilities where we cannot have a probability outside this interval. And with a bit of algebra, I guess it's going to be useful at some point, we create the log odds. We create the log odds for the simple reason that we now have a linear relationship. It's the same as this, but if you plot, use a couple of colors. If you plot red against orange, if you plot red against orange, you get this. And I'll use the same colors again. If you plot red against orange, you get this. It's not linear, but that's by design. With a bit of algebra, rewriting the relationship this way, if you plot pink against green, we can keep that orange. If you plot pink against orange, instead of red against orange, it's now pink against orange, it is a linear relationship. So actually, in many ways, you could use linear regression, couldn't you? And this might be the goal of the book. So the idea is that since it's a linear relationship, I'm going to use color blue. Increasing x by 1 unit, so increasing this by 1 unit, whatever the value is of x, whatever the balance is, so $5,000 balance, increases the log odds by beta 1. So it's that linear relationship, right? And this is everything. The book does tend to repeat at times, and I think we can safely move on to the mathematics now. Estimating the regression coefficients. I know I keep saying this every session, but I'm going to say it again. We had estimated in simple linear regression beta naught hat and beta 1 hat using these two formulae. Those two formulae give you the beta naught and beta 1 coordinates that minimize the RSS surface. You can even see it in this contour plot. And this was using derivatives on the RSS. So we define this variable, which is the sum of the residual sum of squares. And the goal was to minimize it. And I keep on saying that, and I keep on saying it, and I keep on saying it. And it's good to keep it in mind so that we can have maybe a reference point. For now, chapter 4, where we're working on a classification as opposed to a regression scenario. The coefficients beta naught and beta 1 in 4.2, this is logistic regression, are unknown and must be estimated based on the available training data. In chapter 3, we use the least squares approach to estimate the unknown linear regression coefficients. Although we could use nonlinear least squares to fit the model 4.4, and this is kind of what I mentioned earlier, I guess we can use linear regression over here because this is a linear model. The more general methods, this is probably something that we're going to use beyond this chapter, of maximum likelihood. Heads up, my experience, this is extremely important for your actuarial exams, for university, and in real life, of course. It's preferred since it has better statistical properties. I think we're going to look at things like the bias in the estimator. The basic intuition behind using maximum likelihood to fit a logistic regression model is as follows. So let's have a look. It's probably worth spending some time on this. We seek estimates for beta naught and beta 1. So those will be your hats, such that the predicted probability, in this question, it's of default. It could be of sickness, it could be of marriage, it could be of pregnancy, you name it. The predicted probability, p hat xi, xi is your ith observation and your training dataset. For each individual using 4.2 corresponds as closely as possible to the individuals observed. Let's use pink, default status. So it's again this common theme of actual versus expected. Your actual is the pink. You will have this data for your training set. The pink is what your model is predicting, but we're going to pick a beta naught hat and a beta 1 hat that actually best have the green and the pink approach each other. In other words, we try to find beta naught hat and beta 1 hat such that plugging these estimates into the model for P of X. Now, I read it as P of X, but remember, it actually means probability default given X. Given in 4.2 yields a number close to 1 for all individuals who defaulted, and a number close to 0 for all individuals who did not. This intuition can be formalized using a mathematical equation called a likelihood function. I think it looks more complicated than, well, I mean, it's easy for me to say that, but it's actually quite simple. It's quite simple. So we are, instead of defining the residual sum of squares, the RSS, and instead we're defining the likelihood based on beta naught and beta 1. And all we're doing is the following. Might be worth looking at it in Microsoft Word, especially if, let's see, is Word open? It isn't. Just give me a second, please. And I'll share it when it loads. So what we're saying here is, well, first of all, a word on never actually, that doesn't work, and that doesn't work. So that's because when you do this, no, I think it's the Word file. Just 1 second, let me go all the way up. That's funny. Or is it lowercase? Oh, it's lowercase. So what if I do prod? Okay. So you may or may not have seen this elsewhere, but I'll just give you a quick example. So what if I were to type? What if I were to type Mm, can I give you an interesting one? What if I were to type this from, for instance, 1 to 5? Now, how familiar are you with this kind of notation? It's not too difficult. All that it's telling us is this is your generic term, and you're going to multiply it 5 times, 5 minus 1, and then you always add a 1. 5 minus 1, and let's actually change it. Let's make it a bit more general. So, for example, from 6 to 9. This is how many we're going to multiply. How many values? We're going to multiply 4. 9 minus 6 is 3. And you always add a 1. Which 4 values are you going to multiply? Sine x on 6, sine x on 7. You get the picture. Sine x on 8, and sine x on 9. I'm writing identity because it's for any value. Don't let it. You could easily get away with writing equality, but strictly speaking, it's for any value of x. It's for any value of x. So that's what the uppercase pi notation gives us. Now what we're doing over here is, you remember from your secondary school mathematics, when you did probability, you learned the AND rule. AND is multiplicative. So for example, what's the probability? If two events are independent, they're independent, so one of them occurring doesn't influence the likelihood of the other one occurring. So for example, I roll, I don't know, I flip a coin and I roll a dice, and they're not interacting with each other, and then you'd have questions like, what is what kind of font is that? What is the probability, however you spell probability, what's the probability of rolling whatever, of rolling a 2 and obtaining heads? Well, they're independent of each other. We love independent events. The mathematics is a lot easier, and you just compute them. Individually. So you have 1/6 and 1/2, and you have a 1 on 12 probability. I'm just saying this because we're doing the same thing over here. What we're saying is, we're asking, well, we have a probability. Now the indexing is slightly different. The example I showed you uses this indexing from 6 to 9. Instead, this indexing is, all it's telling you is, all those observations, these are people, right? Borrowers. We're looking at a data set with 10,000 borrowers. All those observations who did default, all those observations who did default, sort of whose I corresponds to a yi of 1, and all those observations who did not default. And let's see if I'm getting this right. So the likelihood is the likelihood of default, I guess. So you have the probability default, yes, given this information. And why are we doing 1 minus? Well, that would be the opposite, right? The probability if you do 1 minus. 1 minus the probability. 1 minus the probability default given. Yeah. Do we? I think I'm making sense of this. So what we're saying is we're multiplying 10,000 probabilities over here. Yeah, we're multiplying 10,000 of them. One probability for each observation, but only these defaulted. Yi equals 1, that's a default. So you're multiplying, I think it was 333 that defaulted. So you're multiplying each of their probability. You're multiplying 333 probabilities over here. The probability of what? The probability of default. And over here, you're multiplying the remaining. It's like 9,600 roughly. You're multiplying 9,600 probabilities. These did not default. So we don't speak of probability default, but we speak of 1 minus the probability of default. Don't worry. I'm sure the book is going to do a better job than I have right now. And the idea is you want to maximize the likelihood, right? I don't know if intuitively this makes sense, but you want a beta naught and a beta 1. You want a beta naught and a beta 1 that maximize the likelihood, because you know this happened. This happened. So in our world, we're looking at the data, and this is data that has happened. It's historic. It's in the historical record. So we know, okay, this happened. So since it happened, let's assign it the highest probability. We're kind of retrospectively saying, if it happened, then it had the highest probability of happening. It gets a bit philosophical on this level, but I'll just say it again. Since you have 10,000 observations, it's not like one observation. You have so many of them that you're expecting that the bulk of your data reflects not some kind of outlier effect, but like the actual probability distribution. So you have 10,000 of these, you multiply the probabilities, you multiply all the probabilities, and then you say, well, the number I'm getting here, I want to parameterize on beta 1 and beta naught. So I'll maximize the likelihood. This is the method. This is the method. We're going to do. Right now it's a bit abstract, but we're going to add layers of specificity based on this model. It's going to be much clearer once we progress. Maximum likelihood. Did I skip anything? No. These estimates are chosen to maximize the likelihood function. Maximum likelihood is a very general approach that is used to fit many of the nonlinear models that we examine throughout this book. So let's try mastering it. In the linear regression setting, the least squares approach, oh, interesting, is in fact a special case of maximum likelihood. So you can arrive to the same answers given to you by these squares through this maximum likelihood that we're being introduced to right now. The mathematical details of maximum likelihood are beyond the scope of this book. However, in general, logistic regression, and other models can be easily fit using a statistical software package. That's why we're using R. And so we do not need to concern ourselves with the details of the maximum likelihood fitting procedure. Okay, that we could have a look. Again, how much do we want to deviate from this book? Table 4.1 shows the coefficient estimates and related information that result from fitting a logistic regression model on the default data in order to predict the probability of default equals ES using balance. We see that beta 1 hat is that value, and it's not 0. We're going to go back to the same themes that we had in chapter 3. Is this statistically significant? This indicates that an increase in balance is associated with an increase in probability of default. Now do remember, this is a non-linear model. In fact, to be precise, a 1 unit increase in balance does not increase your probability by 0.0055. Instead, it increases the log odds. It increases this, or I beg your pardon, the log odds, this. So you've estimated your beta 1 hat, 0.0055. So increasing X by $1 increases the log odds by 0.0055. Obviously, if you just do substitute formula, you can easily find the increase in PX. So we're back to, oh, look at this. It's not a T statistic, it's not an F statistic. I guess the book is going to introduce us now to the Z statistic. And as always, if P is low, then H naught must go. It is one way of remembering. For low values of P, you reject the null hypothesis. The null hypothesis is that balance, knowing a borrower's balance, does not give you information on their likelihood of defaulting. In fact, as you would maybe expect on first inspection of this chart over here, maximum likelihood is telling us to reject that null hypothesis. So rejecting it means that actually, yes, balance is a relevant piece of information to have us understand better the likelihood of a borrower with a specific balance defaulting on their loan. Many aspects of the logistic regression output shown above are similar to the linear regression output of chapter 3. For example, we can measure the accuracy of the coefficient estimates by computing their standard errors. The Z statistic in table 4.1. So even if this is really small, and it's just quite small, isn't it? But relative to its standard error, I mean, small means nothing, right? Me telling you this is small. I hope that your inner voice is kind of challenging my statement as a nonsensical one. But relative to the standard error, it is very beg your pardon. Although it might look small, but that means nothing, relative to your standard error, it actually gives you a Z statistic of 24.9. And Z is probably a normal distribution. We'll have a look. The Z statistic in table 4.1 plays the same role as the T statistic in the linear regression output. For instance, the Z statistic associated with beta 1 is equal to beta 1 hat, this divided by standard error of beta 1, And so a large, absolute value of the Z statistic indicates evidence against the null hypothesis. The null hypothesis is beta 1 is 0. This null hypothesis would imply that the probability of default given X is just this. X does not feature. So the probability of default does not depend on the balance. Since the p-value associated with balance in table 4.1 is tiny, we can reject H0. In other words, we conclude that there is indeed an association, and that's kind of what you're after. You hope that with the available info that you have, that there's at least one or more of the variables that do give you a statistically significant relationship with the variable that you're trying to predict. The estimated intercept in table 4.1 is typically not of interest. Its main purpose is to adjust the average fitted probabilities to the proportion of ones in the data. And this means, if I go into decimals just to see what time it is, we said we'll only do half an hour. I wouldn't mind doing another 15 minutes. Do you want to take a vote, or shall we call it a day? If one of you tells me call it a day, we'll do that.
If you guys want to continue, but I think we're gonna go because I have to sleep.
Let's continue tomorrow. Let's continue tomorrow. It's late as it is. Okay, I'm just gonna stop recording.